We're now going to take a look at how to find the relative extrema for functions of two variables. So surfaces of the form z equals f of xy. Now, there's a lot of similarity actually with the process that we're going to describe now and a process that was used in your first semester of calculus. And I just want to remind you of that because, again, if you have a sense of what was done in the past to solve this particular problem, I think it can help us appreciate what we need to do for these types of functions. So just as a reminder, I am going to draw a curve that's nice and differentiable. I'm going to call it y equals f of x, right? And basically, we came up with lots of, not lots, but a couple techniques for finding and classifying these special points. These points where your curve, reaches a high point or reaches a low point. So the high point, we call those either relative or local maximums, right? And then the low point would be relative or local minimums, right? So high points are maxes, low points are mins. And let's see what we can establish about this. Well, at this point, our tangent lines would be horizontal, right? So what that means is our first derivative would have to be equal to 0. Like that, right? But again, just having a first derivative that's equal to 0, that does not distinguish between the maxes and the mins, so we need some other criteria. And the two big criteria that were used, we had the first derivative test and then we had the second derivative test. Now I'm just going to focus on the second derivative test because it says if your function, your first derivative is equal to 0 at a point, and if your function is concave down on the interval containing that same point. So if the function is concave down, remember that means the second derivative would have to be negative, right? So your first derivative is 0, your second derivative is negative at that point, and these two facts allow you to conclude that this critical point has to be a relative max. And similarly, again, using the concept of concavity, if your function is concave up on an interval, right, like for all values of x here, your function is concave up, and somewhere in that interval, the first derivative is equal to 0. So again, if I have this, now for it to be concave up, the second derivative has to be greater than 0. So the second derivative test says if you have and we call these stationary points where your first derivative is equal to 0, if you have a stationary point in some interval where your function is concave up, then that stationary point has to be a relative min. Similarly, if you have a stationary point in some interval where your function is concave down, then that stationary point has to be a relative max. Unfortunately, there are times when this process yields no information, and it happens when functions look like this. So when you have a function like this, you could still have a stationary point, right? So your first derivative is equal to 0 at that particular point. But at this point, because the function has an inflection point, then it's neither concave up nor concave down at that point. Like it's concave down here and then concave up there. So what happens is it turns out that your second derivative is also 0. So when that happens, basically, the second derivative test is inconclusive. So I can't state anything definitively based on these two facts. In fact, I can't even say that it's an inflection point. I have to establish that there is an actual change in concavity before I could do that. So these two equations alone, they don't allow me to conclude anything definitive. And unfortunately, we'll see a version like this when we talk about these functions of two variables, right? But this is just a reminder. I know it's like a 5-minute reminder of Calc 1, but it really is important to see this, because this is the concept that we're going to build on, right? So let's go ahead and just make some definitions, right? So let's write down some definitions, and that way we have the terminology. Now the terminology is going to be very similar. There is a new word that didn't show up in Calc 1, but it's here now. So let's just go through and define. So a function f of xy has a relative minimum. Right, so this is what we're defining at, let's say, x0, y0, if all the points on the surface are greater than or equal to the point on the surface that corresponds to x0, y0. So if your surface, all the surface values are greater than or equal to the surface value at that specific point, then at that specific point, the function is said to have a relative minimum. Now, for it to be relative, we can say for all xy in some region around, let's use the word around, x0, y0, right? So it's not for all x and y, but this whole idea in some region around, that's like when you kind of you're zeroed in on a particular part of the surface and you see that it kind of bottoms out. It has a specific low point in that particular region, and we refer to that low point as a relative minimum. And then similarly, a function f of xy has a relative maximum, right? So now a relative maximum at x0, y0 if all your surface values, right, the values on the surface are less than or equal to that specific surface value at that point. Again, for all xy in not is, so in some region around x0, y0. So those are your peaks, right? Well, as we saw, we have another type of phenomena, and that's those pesky saddle points. So let's define what a saddle point is. Again, not super formal, but just to get an idea of what it is. So a point on our surface f of xy is called a saddle point. And what happens at these saddle points? Well, if it is a minimum in let me say it like this, and let me clean this up a little bit. So if it is a minimum when approached from one direction but a maximum when approached from another direction. So, but a maximum when approached from another direction. So that's why at one particular, at a saddle point in one direction, the surface would be sloping upwards. And then in another direction, the surface would be sloping downwards. So saddle points are neither minimums nor maximums. It's like this weird kind of twisting of the surface, where in one direction, the surface is going up from this point, and then in another direction, the surface is going down from the same point, right? So those are some definitions. Couple other definitions as well. So we want to also define what we mean by a critical point, right? So let's define a critical point. So the point x0, y0 is a critical point if either one of two things happen. The first thing, so if either the partial derivative with respect to x evaluated at that point is equal to 0, and the partial derivative with respect to y evaluated at that point is also 0. So this definition here is analogous to how we define a critical point in Calc 1, where the first derivative has to be equal to 0 or something else, which is going to be the second case here. But for those stationary points, the first derivative has to be equal to 0. Well, now we have two first derivatives, and we require them both to be equal to 0. So that's one way you can have a critical point. Or the second way, the other point now is where you have those sharp corners, and that's where at least one of these would be undefined. So, or at least one of fx x0 y0 or fy x0 y0 is undefined, right? And that's how we define critical points. So that's similar, right? So a lot of the terminology is very similar. The saddle point is new. Now, before we state the big theorem that allows us to classify these critical points, now that we know how to find them, right? We know that we're going to have to set our first partial derivatives equal to 0, and we're going to be solving for x, y. Well, after we find this ordered pair, then how do we know if it's a relative min, a relative max, or a saddle point, right? So I'm going to define yet another thing. So this is called the Hessian, or some people refer to it as the Hessian, but the Hessian, right? And this is it's uppercase H because it's named after a mathematician whose last name was Hess, so they just call it the Hessian or Hessian. So the Hessian of our surface fxy is the following matrix. So there's something we're going to do to this function and actually form a matrix. So following matrix, and it's just denoted by H. And this is what it is. It is a matrix, and what you do is you fill it out with all the possible second partial derivatives. So it's going to be your fxx in your first column, first row, and then your fxy, second column, first row, and then your fyx in your second row, first column, and then finally fyy. That's your in your second row, second column. So this matrix is called a Hessian of this particular surface. So let's just do a quick example of just computing the Hessian. So let's do a quick example of this. So let's say our surface is something simple like e to the x sine of y, right? So I have to go through and find all the possible second partial derivatives. Now remember, there's that theorem, Clairaut's theorem, that says, well, if your mixed partials are continuous, right, then these two are always going to be equal, the fxy and the fyx. Now looking at these two functions, right, the e to the x and the sine of y, these functions are always continuous and their derivatives are always continuous. So we would expect these to be equal for us, right? Let's go through and compute them. So let's do our f sub x, differentiating with respect to x, treating y as a constant. That's e to the x sine of y. And then I'll just go ahead and do my fxx there, same line. Well, it's the same thing, right? Same function. Differentiating with respect to x, treating all the sine of y as a constant. We'll have e to the x times the sine of y. Let's do the f of xy. Well, so now take this function and differentiate it with respect to y. That means I'm treating x as a constant, so I'll have e to the x, and then differentiating the sine of y with respect to y is going to give us the cosine of y. And this is what we would expect when we go through and do yx. So let's now do the y's. So f sub y, e to the x is treated as a constant. Derivative of the sine of y is cosine of y. So e to the x cosine of y. Then let's do our y, not the mixed one. And differentiating this with respect to y again is going to give us negative e to the x sine of y, because the derivative of cosine is negative sine. So negative e to the x sine of y. And then when we do our mixed in this direction, yx, take this function and differentiate it with respect to x, and you see we get the exact same thing, e to the x cosine of y. And that's what we would expect to get. So having now our 4 second partial derivatives, here is the Hessian, and technically it is also a function of x and y. So I'll go ahead and indicate that, but now it's like we're using functions to fill out our matrix. So in this position, we're going to put our fxx, so this is e to the x sine of y, and then in this position we're going to put our fxy, so that's e to the x cosine of y. And then in this second row, first column, we're going to put our same e to the x cosine of y. And then finally in the y, in the second row, second column, we're going to put the function negative e to the x sine of y, and then we're going to close our matrix. And this is the Hessian for this particular surface, right? And this h, in fact, the determinant of this h is going to play a significant role in how we actually classify points as relative mins, relative maxes, or saddle points, right? So I just wanted to do the Hessian there. And then I think we now have all the ingredients that we need to state this all-important theorem. And It's not something that we can prove. It requires some advanced calculus techniques. So we're going to state our theorem. And basically what this theorem is, it is the second derivative test. So it's the second derivative test for functions of two variables, right? And it's going to allow us to classify all these interesting high points, low points, and saddle points. So here we go. So let's say this. Suppose, let's say x0, y0 is a critical point of our surface fxy, and all second partial derivatives, so all second partial derivatives of f of x comma y are continuous, right? Continuity is important there. So continuous on some region, so let me scroll down here, on some region containing this critical point x0, y0, and yeah, so that's the part of it. We have our critical point, and we know that the second partial derivatives are all continuous. Define d of xy to be the determinant of the Hessian, right? So that matrix, this 2x2 matrix that's right here, we're going to use D to stand for, to represent the determinant of that particular matrix, right? And because that matrix has all the second partial derivatives, it has all the information that we need in most cases that will enable us to classify the different, the critical points as either mins, maxes, or saddles, right? So here are the four possibilities. So if our D, which is this determinant, evaluated at our critical point is greater than 0, and fxx, just the second partial with respect to x, if that evaluated at the same critical point also produces something greater than 0, then our surface fxy has a relative minimum at that point, so at x0, y0. So this is basically saying, both of these, with the determinant of the Hessian being positive and the second partial with respect to x being positive, it's almost like saying your function is concave up, right? Both of these, or I should say, your surface is concave up, which would then make the critical point a relative min. So that's the similarity, right? But it's a little harder to justify that. Next, if our D evaluated at x0, y0 is greater than 0, and our fxx evaluated at x0, y0, if that is negative now, then our surface has a relative maximum at our critical point, right? So again, this is like the surface is concave up. This is like the surface is concave down, which in that case would lead to a critical point that's a relative max. The third possibility is if your D happens to be negative, right? And you don't even have to check the fxx in this third case, but if the determinant of the Hessian evaluated at that point is negative, then fxy has a saddle point. So that's where you get that strange twisting of the surface. So as a saddle point at our x0, y0. And then the only other possibility now is if your D is 0. So unfortunately, if the determinant of the Hessian is equal to 0, then no conclusion can be made. Just like how if your second derivative just comes out to be 0, where it means your test is inconclusive, same thing here. So I'll just say this: no conclusion can be made. In other words, this fourth possibility, if your D comes out to be 0, then the critical point may be a relative min, it may be a relative max, or it may be a saddle point. We just don't know. And other techniques would have to be used, and those techniques go beyond the scope of this course. So if our D comes out to be 0, we're just going to say no conclusion can be made. And that's the theorem. So it's a pretty lengthy theorem, but it tells us everything that we need in order to find and classify all the possible critical points, right? So I think what we can do is just, let's do an example illustrating this. Right? And we'll do a relatively short one because these problems can be pretty lengthy, but this one will sort of illustrate the overall process. So here it is: find and classify all critical points of, and then here is our surface. So fxy is equal to 6x squared plus 6y squared plus 6xy plus 36x minus 5. All right. So obviously we're going to find them first and then classify. So now for this type of surface, this is a polynomial, and we know that polynomials always exist. Even when you differentiate them, right? Their derivatives always exist. So the only way this particular surface can have a critical point is if both first partial derivatives are equal to 0, right? So let's go ahead and find our fx. So in this case, we're going to end up with 12x. This term is a constant, so its derivative is 0. Again, we're treating the y as a constant, so when I differentiate 6xy, I'm going to get plus 6y, and then differentiating this with respect to x gives me 36, right? So that's our first partial with respect to x. Let's write down the first partial with respect to y. The first term differentiates to 0, the second term differentiates to 12y, the third term, because I'm treating x as a constant, and that 6x is multiplying our y, its partial with respect to y is 6x, and the two last terms both differentiate to 0 because, again, we're treating x as a constant, right? So to find the critical points, so for critical points, what has to happen is both of these derivatives have to be equal to 0. So our fx is equal to 0 and fy is equal to 0, because both of these derivatives always exist, right? So the only way you can have a critical point is if they're simultaneously equal to 0. So what that means is we actually get a system of equations to solve, right? Because now we're going to be solving for an ordered pair or several ordered pairs depending on the surface, but that has to be equal to 0, and then our 12y plus 6x has to be equal to 0. Now, we have lots of ways of solving linear systems. I'm just going to do it the old-fashioned way, where I'm going to look at equations and see if I can, eliminate anything easily. Here, what I can do is I can actually solve for x. So from the second equation, I can solve for x. So 6x is negative 12y. So then x is negative 2y, and then I can substitute this into the first equation and eliminate the x, and then I'll be able to solve for y, and then once I know y, I can come back to this equation and get x, right? So substituting negative 2y for x in the first equation, this gives me negative 24y plus 6y plus 36 is equal to 0. So I have negative 18y is equal to negative 36. So y has to be equal to 2. And if y is equal to 2, then x is equal to negative 4. So in this case, this surface has only one critical point, right? So I'll just say this, fxy has only one critical point. And what is that point? It's the ordered pair negative 4, 2, right? So then now the question is, at this point, does the surface have a peak, a high point, or a low point? Or does it have one of those, interesting saddles? Well, this is where the second derivative test comes in, right? So what we're going to do, we are going to, let's see this. Let's go ahead and compute the Hessian. I'm going to go up here so that way we can see the first partial derivatives. So fxx, that's equal to 12. Everything else is a constant, so we're just left with 12. fxy, if I differentiate this with respect to y, well, I'm just going to have 6. And then let's do fyx. Well, that's also 6, and we expect these to be the same because, as stated by Clairaut's theorem, these mixed partials are going to be equal as long as everything is continuous, and polynomials are always continuous. And then fyy, differentiating this with respect to y, we get 12, right? So what happens here is that all the second partials are constant. So that means our Hessian matrix is actually a constant matrix. So I'm going to write it down anyway. So here's our Hessian. And it is 12, 6, 6, and 12. And then right below it, I'm going to write down the D. So the D is also going to be a constant. And that's just a regular determinant. It's 12 times 12. So that's 144 minus 36. Oh, I wrote 38, but I meant 36. And then that's equal to, what's that? 108, which is positive. So because these all these entries and our D comes out to be constants, and it's really easy to apply the test. I'm going to write it down as if we were evaluating, but because these are all constants, we know what the evaluation is going to be. So in fact, yeah, let me take this off here. I mean, yes, it's always positive, but what we would do is now we would then take our critical point, evaluate it at D. So we're going to first check our D. In this case, we know what's going to happen. It's going to be 108, which is greater than 0. And whenever D is greater than 0, then we have to check our fxx. So we're going to check our fxx, also evaluated at the same critical point. But fxx is always 12 because it's a constant, always positive. So whenever D is positive and our second partial with respect to x is positive, then it means at this location, at this point, our surface has a relative minimum. So therefore, at -4, 2, fxy has a relative minimum. And that's because at this point, this information tells us it's almost like our surface is concave up. We don't really define it in that way, but that's the similarity with what would have happened in Calc 1. If we wanted to know what the actual minimum z value is, then we would have to evaluate this in our original function, right? So just as a point of clarification, so the value of the relative minimum is, and it would be f of -4, 2. So you'd have to evaluate it. So then you'll have your 6 times -4 squared, and then plus 6 times 2 squared, and then plus 6 times -4 times 2, and then plus 36 times -4, and then minus 5, which comes out to be -77, right? So that's this is where the relative minimum occurs, and this is its value. And there you go. So that's the process. It's a little lengthy, and depending on the surface, you might have a little bit more algebra to do and when solving those systems simultaneously. But now we have a very specific technique for finding and classifying these relative extrema of functions of several variables. See you in the next video.